Welcome to today's video that will go through a bit of a sidetrack from what we've been doing. So we are doing a unit on polynomials, and we just got into the binomial theorem. What we're going to look at today is some more probability and statistics type terms and concepts. However, they're going to be necessary for us to draw some details back in that'll let us tie it back in with the binomial theorem. So you're going to have to bear with me here for the first part of the video as we're going to go through, as I said, some counting principles and something called permutations and combinations. And then this information will get tied back in with the binomial theorem. All right, so we're going to start out and we're going to talk about something called the fundamental counting principle. Nice little principle to understand. It is a way to basically tally up total outcomes. So they refer to it as the multiplication principle. And the key word in this principle is the word and. If you want event A and then event B to happen and then event C to happen, well, the number n stands for the number of ways. So the number of ways for event A and then event B to happen is however many ways event A can happen multiplied by the number of ways that event B can happen. Now, how does that become useful here? Let's suppose that you were going to fly from Toronto International Airport, and there was 4 different ways to get to Montreal, and then there was 2 different routes to get from Montreal to Halifax. Now, ignoring the whole connection times and anything like that, we'll assume that they would all connect together if needed. It says how many different ways are there to get from Toronto? Well, there are a number of ways to get from Toronto to Halifax would be the number of ways because you can't get directly to Halifax. You got to go Toronto to Montreal first. You say, well, how many ways could I do that? Well, I could get on 4 flights. Then I've got to go from Montreal and I have to fly to Halifax. So how many ways could I do that? There's only 2 different routes. In total, there would be 8 different flight paths that we could come up with. And that is referred to as the counting principle. I don't want to look at the addition one. So then I want to look at, this is a common one with license plates. I don't know if you've ever asked yourself this, but I wonder how many license plates there would be possible in certain states or provinces or whatever it is that you're talking about. It says here that the license plates in Vermont consist of 3 digits and 3 letters. So for example, and it says given that the digits and numbers can be repeated. So your license plate could be something like this. So 3 digits, let's say it could be 3, 3, 5, J, K, K. So that could be a license plate. This is just an example. So I want to know how many different license plates could I do if this were the combination of patterns that were allowed. Well, if I wanted to get the total ways that something can happen, start with this first number. Say, well, how many different ways could you start and come up with that number? And the answer would be 10, because you could use 0 as well. So 0 to 9 would be 10 possibilities. 0 to 9, there's 10 more possibilities. And the reason it's 10 is because you're allowed to use 3 again. 5, there'd be 10 possibilities for that number. Now we're on to letters. When we're dealing with letters, there's 26 possibilities. And then there'd be 26 possibilities for this letter. And then there'd be 26 possibilities for this letter. So now if we just grab a calculator. So according to my calculator, I get a total of 17,576,000 different license plates that would be possible. So if you think of the province of New Brunswick, actually this is the exact same system we use in New Brunswick, except I think, well, it's the other way. The letters are first, so it could be something like JNP 423 or 434, whatever. That could be your license plate number. Exact same system. 3 letters, 3 numbers. It doesn't matter the order you had these in, because it would just be these numbers reshuffled around and multiplied together. You're still going to get that. So in New Brunswick, on our system, we could have a possible 17,576,000 576,000 license plates. In the province of New Brunswick, we have approximately 750,000 people. I think having 17.5 million license plates will suffice. So that system would work. Now it says, what if you weren't allowed to repeat letters? So you couldn't have the same letter, like you couldn't have KK and you couldn't have the same number. How would that change things? Well, so I'll just put here, no repetition allowed. Let's think how this would change. Well, let's suppose we go with this one, or let's go with the letter like this one. So here's New Brunswick. First letter, you'd have 26 choices. Now, whatever letter you chose here, you're not allowed to use it again. So when you go to pick your next letter, instead of having 26 choices, now you're only going to have 25. When you go to pick your next letter, you're going to only have 24 now. Hit your digits. So the first digit that comes out, you'd have 10 choices. You've now picked one of them, so you can't pick it again. So now you're only going to have 9 choices. Then your last one, you're only going to have 8. So under this system, as you can tell, because some of these numbers are smaller, we're going to have fewer possibilities. So I'm just going to do this calculation. That calculation gave me 11,232,000, which, as we expected, is fewer possibilities. All right, so that's what we call the fundamental counting principle, or sometimes they just call it counting principle. I want to show you another little symbol before I do a quick little blurb about the lottery here. This symbol in math is called a factorial sign. It's one of my favorite stories about a student a few years back. So I put this up on the board just to see if anyone had heard tell of it or saw it before. So I put this up on the board, and a student, I said, "Has anyone ever seen this? Anyone know what it means?" And at the top of their lungs, someone yelled, 6! Meaning the exclamation point meant the same thing that it did in an English passage. It was funny, but that's not what it means. It doesn't mean to put emphasis on the number 6. It means what you see below here. It's called factorial. There will be a factorial button on your calculator. It will usually have an N with that beside it. Now, it might be a button or it might be a second function, but there should be a factorial button on any scientific calculator. You may have to go into a math. If there's a math feature, you might have to go into that. If you have a probability feature, you might have to go into that. So it might be hidden in that menu. But if it's a scientific calculator, there is a factorial button there somewhere. When you hit 6 factorial on a calculator, what it does is take 6 times 5 times 4 times 3 times 2 times 1, and it gives you the answer. It multiplies this by every natural number below it. 8 factorial would be that. 27 factorial would be 27 times 26 times 25, till you multiply by 1. That's referred to as a factorial. Now I'm showing you that. Let me see. So if I had 12 factorial and I wanted to divide by 8 factorial, well, 12 factorial is 12 times 11 times 10 times 9 times, and then 8 down. Well, 8 multiplied by everything below it is the same thing as 8 factorial. Then I'd have an 8 factorial on the bottom. Those two would cross each other out. So I could calculate this a little bit easier than doing this all out, getting the answer here, dividing the two. Instead, I would just do that calculation to see that it's 479,001,600 possibilities. This factorial symbol is going to be part of a formula I'm going to show you here in a moment. Before I get to that, though, I always like to give students a reality check here. Let's suppose you thought, I think I'll just take my chance on winning the lotto. Never mind this school stuff. Well, let's go through your chance of winning the Lotto 649. If you're not sure how this works, there are the numbers 1 to 49 in a drum. You have a ticket with 6 numbers. So number, one more. 1, 2, 3, 4, 5, 6. So you have 6 of these. they don't repeat. So you could have something like, I'll give you an example of a 649 ticket. Your numbers might be 4, 6, 24, 10, 46. So it's between 1 and 49, including 1 and 49. I don't know, whatever, 30. That's my 649 ticket. You say, I wonder what my chances of winning are. Well, you've got one set of 6 numbers out of, I wonder how many are possible. This is where counting principle can help. Here, when you pick that first number out of the drum, so it's like bingo. The numbers 1 to 49 are bouncing around in there, and you're going to pick one of them out. Well, if you pick one out, you've got 49 different numbers that could come out. Now, once the number comes out, it doesn't go back in. So then the next number that comes out, there's 48 possibilities. Then 47, 46, 45, 44. 1, 2, 3, 4, 5. There's your 6 numbers that come out. Well, let's do a calculation on that and see what we've got for possibilities. Well, here's what came back as an answer. When I multiplied that out, I got 1 point this multiplied by 10 to the 10th power. So if you move that decimal place 10 places to the right, there's how many possibilities there are of 6 numbers being drawn if you've got 49 numbers in the draw. 10 billion, 68 million, and a whole bunch. Your chances of winning are not very good. So there's an example of where I use counting principle to figure out my total number of outcomes. There's another draw called Lotto Max. You may have heard tell or seen these signs as well. It's essentially the same thing, 1 to 49. Here's the only difference. Instead of 6 numbers right, you need to get 7 numbers right. Well, it's going to be the exact same as this, except times another 43. So that times 43, which is why it's much more difficult to win Lotto Max than it is this one. Both are extremely, extremely difficult. Lotto Max is even worse because you've got to get 7 numbers right instead of just 6. So that's kind of a practical look at how you can use counting principle. This leads us into 2 terms that I'd like you to become familiar with. They're called permutations and combinations. You'll see here we're going to use factorials in these. It says how many distinct lines could be formed from a group of 8 people. So imagine that we're sitting in the class and I said there's 8 of us. Back in the old elementary school days where you loved to stand and get in line at the door. Some students still love to stand and line up at the door. How many different ways, if I had 8 people in the room, could they go and stand in line? Well, think about it this way. So we bring the 8 people up, we put them at the front of the room and said, okay, let's go line up. When I look over and I get to pick someone to put in line first, how many choices do I have? Well, there's 8 of them, so I've got 8 choices. So I say, okay, you go get in line. I come back to my group and say, how many do I get to pick from now? I've got 7 choices. I go back, then I get 6 choices, then 5, then 4, then 3, then 2, then 1. This could be found using the factorial button on your calculator. So if you hit 8 factorial, let me dig out the factorial button here on my calculator, and 8 factorial, when I did that calculation on my calculator, just to get it out here and see it, was 40,320 different possible ways that I could put people in line. And sometimes students are amazed at that. They say, really? 8 students in a room, there's 40,320 ways that we could put those in what are called distinct, meaning different lines. If there was 5 people, it would be the exact same thing, except now we would say, oh, well, the answer's 5 factorial, which would be whatever. So hopefully you've at least found the factorial button on your calculator. And then there's going to be another button that hopefully you'll find on your calculator here in a moment to do what are referred to here as permutations and combinations. So this was just to jar our memories on those buttons on your calculator for factorial. On the calculator I was using, it wasn't n factorial, it was x factorial. And it was a second function. It was above, it doesn't matter. It was above my negative x to the negative 1 key. But they're different in all calculators, so there's no, you may have to hunt it down and try and find that button. This leads us into what are called permutations. And permutations are used when you've got a group of items and you want to pick a subgroup, a smaller group out of it. So for example, if I had a class of 12 students and I wanted to pick out a class executive, a president, a vice president, and a treasurer, that means I'd want to pick a group of 3 out of a group of whatever the class size of 12, I think I said it was. So that would be an example of a permutation, where you pick a smaller subgroup out of a larger group, and it's called a permutation if you're concerned with putting the things in order. If you're not concerned with putting the things in order, we call it a combination. All right, so it's permutations and combinations. That's the only difference between permutations and combination. Combinations, you don't care the order you put them in, and permutations, order matters. I'll give you an example. I'll use the class executive one again. So we've got 12 students, and we need a group of 3 to be the president, the vice president, and the treasurer. Well, if I pick a group of 3 students, student A, student B, and student C, that group, depending on who's the president, who's the vice president, and who's the treasurer, could be a different arrangement if I switch things around. So that is an example where order matters. Versus a combination would be this. Class of 12 students. We need 3 students in here to do a survey. So from 12, I need a group of 3. Now all 3 are going to do the same survey. Would it matter what order they get picked in or which title I put on them? Student A, student B, student C are all doing the same thing. They're all, the order that they're in makes no difference. Then it's an example of a combination. Another example of a permutation, a common one is like at the Olympics, when you've got maybe 8 or 10 runners running in the 100-meter dash for the gold medal. The order they finish is going to matter, so that would be, so if you're trying to figure out who's going to get gold, silver, and bronze, out of the 8 runners, you're going to try and pick a subgroup of 3 where the order matters, so you'd want to use a permutation rather than a combination. Now, I'm hoping every once in a while there's someone can't or has a calculator that doesn't have these 2 buttons on there. So you're going to take a moment now and try and find these 2 buttons, NCR and PR. Now on this calculator screen capture I've got, they're both second functions. On the one I have here in front of me, the NCR is on a button, so it looks like this. It has NCR, and then as soon as you find one of them, the other one's right near it. It's either beside it, above it, and then this one's second function is NPR. As I said earlier, you may have to go into math. If you have that as an option, you may have to go into probability is another common one. If you had a key that said probability, it might be hidden in there somewhere. But most likely, if you have a scientific calculator, these 2 buttons are on there. Now, if they're not on there, this one's definitely there. Every scientific calculator has factorial. We have run across the odd one over the last number of years that doesn't have these buttons. If it doesn't have those buttons, unfortunately, you're going to have to memorize a formula. The way to calculate NPR, which means this, N permute R. So if I wrote down, just to translate this for you, if I wrote down 3, let's say 8 permute 3. That means in words, from a group of 8, select a group of 3 where you're going to be concerned with what order you put them in. So from a group of 8, permute, pick, choose, and order a group of 3. Now, order doesn't necessarily mean put first, second, third. Order could mean title them, give them each a distinct color or something along those lines. That's where they mean order. Sometimes students get fooled by that and they think order means first, second, third all the time. It doesn't have to necessarily be that. So n is the number of items possible. R is the number of sub-items you're going to choose. So if you do it using the formula, it's n factorial divided by n subtract r in brackets factorial. Now what I'd like you to learn though is how to use hopefully that button on your calculator. It saves us not having to use that formula at all. So for example, let's see if you can find 6 permute 3 on your calculator. So you actually hit the 6. So on the calculator right here, I hit 6. It'll just show up a big P. So when I do it, it goes 6. It's got a big P beside it on the screen. And then I hit a 3. And the answer is 120. So find that button, the NPR button, permutation button, and just play around with it and see if you can get 120 when you do 6 permute 3. 5 permute 4 gives me 120 also. And if I do 7 permute 2, 7 permute 2, that one gives me 42. So again, this would translate to mean I have a group of 7 items. I want to pick out a smaller group of 2 from that 7, and I'm going to put them in order, or give them a title, or give them some kind of distinction so that I know that they're not all equally part of the group. All right, so those, we're not getting into very much detail in these other than you've heard the words. You'll see these formulas. I'm just trying to give you a bit of background. Foundations 12 would go into this kind of stuff in a lot more depth. We don't here in pre-calc. So combinations, it's the same idea, except as I said, the order is not important. Now, for this situation, then I want you to think about this. If we had the scenario, I'll use the class one. That's an easy example. 12 students in the class, and I wanted to pick out a subgroup of 3 and put them in order, versus a group of 12 students, and I just want to get a random group of 3, don't put them in any order. Which one do you think would generate more possibilities? Well, hopefully you would think it's the one where you have to put them in order. This one, you should get smaller answers. So if I do, for example, if I just go back here, let's look at the formula first. So this time we'd be using NCR, and it's read out as N choose R. That's why it's got a capital C for combinations, but it's also, when you say it out, it's called choose. You will sometimes see this one, N choose R, written like this. N with an R, like that. It'll look almost like a matrix, they call it. So let's say you had 5 choose 3. It could be written that way. Now look at the formula. You may say, oh, it's the exact same formula. It's close, right? N factorial divided by N subtract R factorial was permutations. You've got this extra R factorial down here that you're going to divide by, which obviously should make the answer smaller because you're going to take the same thing you got before, but you're going to divide it by something down here. If we look at these values now, so if I had 5 choose 2, find that button on your calculator. So 5 NCR 2, and I get 10 possibilities. 6 choose 4, 6 choose 4, I get 15 possibilities. Now this one should be obvious, but we'll do it out. 3 choose 1, we get 3 possibilities. Right? Out of a group of 3, how many ways can I pick 1? Obviously the answer is 3. All right, so those are permutations and combinations. As I said, we're not getting into they're really more lend themselves towards probability concepts. However, oddly enough, as you're going to find out here in a moment, they actually do tie in with polynomials and the binomial theorem. So hopefully you've got a kind of a brush over here on factorials, permutations, combinations, and counting principle. From that, we're going to move on and look at different ways of how these can be used with the binomial theorem. Now, if I look at these scenarios just before we go any further, and I just want to identify if we could tell if they're permutations or combinations, and we'll write out a permutation or a combination. We won't actually calculate them. Hopefully you figured out how to do that on your calculator on the last slide. So let's look at the first one. How many 3-card poker hands can be made from a regular deck of 52 playing cards? So you got 52 cards. From that group of 52, you're going to pick a group of 3 and make a poker hand. Do you think the order those cards are sitting in is going to make any difference in regards to the poker hand? So if I deal the cards out to you and you get a king, and a 5, do you think it would have made it any different if I had given you a 5 and then the 2 kings, or a king, a 5, and then a king? No, the order you got the cards made no difference. So this would be an example of a combination. From 52 cards, how many different ways could I choose 3? Order doesn't matter. 7 people are lined up for a tug-of-war team. Lined up is often a giveaway. How many ways can this team be lined up for the contest? Order is definitely going to matter. So what they're saying is, how many different ways could you put someone at the front, change them, put them in the back, put them in the third spots, etc., etc.? Definitely a permutation. You have a group of 7. You're going to pick a group of 7 and order them. So there's the number of ways you can pick a group of 7 from a group of 7. You've got 15 people and they're entered in the 100-meter dash at the Olympics. How many different ways are there to hand out the gold, the silver, and the bronze medals? I mentioned this one earlier. That means the order of the 3 finishers is going to matter, so it's a permutation. There's 15 people in the race, and we're going to pick 3 out of that to be the gold, silver, and bronze medalists. We've got a class of 18 students. We're going to randomly select 10 to participate in a survey. How many different selections are possible for this survey group? So this would be, order doesn't matter. I just need a group of 10. I don't care what order they're in. From 18, choose a group of 10. Okay, so that's how you read a question and interpret whether it's a permutation or a combination. All right, so our little side trip on some probability concepts is now over, and we're going to jump back to the binomial theorem. And we're going to show you a nice, neat connection that was made by mathematicians over time. So our first strategy was to use this triangle called Pascal's triangle. Well, someone noticed that this pattern would have been the first one they come up with. Somebody found that if you did this, if you did combinations of 0, choose 0, 1, choose 0, 1, choose 1, and then you went to the next row and you did combinations, 2, choose 0, 2, choose 1, 2, choose 2, that these values coincided exactly with the values of Pascal's triangle. Now let's look at this pattern. So this is the row you use if you're raising something to the 5th power. Second number in would be a 5. Well, in combinations, if it's the 5th row or something, x plus y to the 5th power, so I would know to go to this row because the second number is a 5. With combinations, you will know that it starts out at whatever the power is, it would be 5, choose 0. Then notice what happens. It's 5, choose, the 0 just keeps going up until you get the same number. So 5, choose 0, 5, choose 1, 5, choose 2, and so on until you get to 5, choose 5. So if I had something to, let's say I had x plus y to the 8th power. It's a bad 8, but that's an 8. How would I get the coefficients that would show up in Pascal's triangle? Well, if I follow my pattern, I would go 8, choose 0. I'm not going to write these all out, but we'll get it started. 8, choose 1. 8, choose 2, dot, 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 right up to 8 choose 7, and then 8 choose 8 would be my last one. Now, anything choose 0 is always 1. Anything choose itself is always 1, because that's saying from a group of 8, how many ways can I pick a group of 8? There's your 1 and your 1. So that's going to always make sure you get 1 and 1. Then these numbers will coincide. So if I look at this and say, well, it's kind of neat, I guess, but big deal. Why is it, so what? Here's the advantage. If I wanted to raise something to the 25th power, I need to write out all the rows above until I get to the one that has the second number in a 25, if I'm going to use this strategy. Using this strategy, I don't need all the ones above it. I just know to start, if it's 25th power, start at 25, choose 0. Now, it'd be a lot of work, but I would just start at 25, choose 0, and work my way up until I got to 25, choose 25. I wouldn't have to do all the ones above it to get to here. That's the major, major advantage to using combinations to get your coefficients rather than Pascal's triangle. So let's put this into play. Now they just show you how this works in general terms. We'll do a specific example here. Let's suppose I wanted to take the binomial 2x minus y squared to the 13th power. Actually, let's do out a whole one first. So let's take 3x squared plus 2y, and I want to raise it. We'll just go to the 4th power just to get the pattern down. Okay, so here's how the pattern would go. The number in front, so I'm not going to use Pascal's triangle. I'm going to go 4, choose 0, and then the first binomial, or the first term of the binomial will be to the 4th, and the second term will be to the 0. Plus 4, choose 1, 3x squared will now go to the 3, and 2y goes up 1, just like the pattern on the variables doesn't change. And then I'll go 4, choose 2, 3x squared, multiplied that one squared, and then it'll be 2y to the 1, that one will be squared as well. Plus 4, choose 3, 3x squared, this one would be cubed, this one would be to the, sorry, I'm going the wrong way. This one would be to the 1, that one would be the 1, and that one would be to the 3. So this one would be to the 1, that one would be to the 3. Remember the checkpoint? 4 and 0 is 4, 3 and 1 is 4, 2 and 2 is 4, 1 and 3 is 4. Now I still got one more to go. So you're not done until you get to 4, choose 4. Now you know you're at the last number. 3x squared will be to the 0. 2y will be to the 4. So now you're going to take your calculator out rather than Pascal's triangle, and you're going to figure out 4, choose 0. Like that one's always a 1. We know the first, it always starts with a 1. So that's a 1. Oh, let's back up for a second. Let's look here for a pattern. If it's 4, choose 0, my terms here are 4 and 0. If it's 4, choose 1, it's 3 and 1. If it is 4, choose 2, it's 2 and 2. 4, choose 3, it's here. 4, choose 4, it's this. Do you notice that this number, right, this number always matches up with this number? If that's a 1, that's a 1. If that's a 2, that's a 2. If that's a 3, that's a 3. That's a 4, that's a 4. Now, that'll be important in a moment when we do a specific term here. So I've got a 1. This is now 3 to the 4th, which is 81. X squared to the 4th, that's x to the 8th. And anything to the 0 is a 1. So that one's just a 1. Plus 4, choose 1. So we might need our calculators here in a second. 4, choose 1 is equal to 4. 3 cubed is 27. X squared cubed is x to the 6th. And then 2y raised to the 1 would just be 2y. plus 4 choose 2. So 4 choose 2 is equal to 6. That's this number. 3x squared would be 9x to the 4th. And then 2y squared would be 4y squared. 4 choose 3. 4 choose 3 on my calculator tells me that that's 4. 3 to the 1 is 3. X squared to the 1 is x squared. 2y cubed, so 2 cubed is 8. And y to the 3rd. Last one. So 4 choose 4 is 1. Anything to the 0 is 1. 2 to the 4th is 16. And then y to the 4th is y to the 4th. Almost there. We tidy this up now. So this one's going to be 81. X to the 8th. This one is going to be 8 times 27. 8 times 27 is 216. So plus 216. X to the 6th y. You can write this out. Some of you may want to do a little bit more than this in your head or on your calculator. So this line could be skipped and you can go right to here. Where am I at? So 9 times 6, so 54 times 4. So 50 and 4 is 200, so that's 216 x to the 4th y squared. Plus 4 times 3 is 12. 12 times 8 is 96 x squared y cubed. 16 y to the 4th. So this one's just 16 y to the 4th. So there is that binomial expanded out using the binomial theorem, but instead of Pascal's triangle, I relied upon using combinations. So the real advantage to that is a question like what you see here. You've got 2x subtract y squared. You want to raise it to the 13th power. Well, if I was going to do this with the binomial theorem and Pascal's triangle, I would need to start at 1 and write out all the rows until I get down to the one with 13. We're definitely not going to do that. We are going to simply do this. We're going to go combination. So I know it's going to be 13, choose something. We'll figure what it is here in a second. Put your 2x here. Put your negative y squared in there. Now I got to figure out what the exponents are here. Well, to get 18, and this being a y squared, I would need to put a 9 here. Now if I go back here, do you remember that whatever number was on the second one also was here? Whatever number was on the second one was here. So as soon as I put a 9 here, I know that it's this term. Do you remember in Pascal's triangle, we had to kind of play around and figure out which number to pick? There's none of that now. As long as whatever I put on this second one, it goes here. Then your 2x would be, so if that's 9, it's going to have to be a 4, right? Because these two have to add up to give you 13. And that's going to work because that's going to give you your x to the 4. So then we will take out our calculator and we'll do 13, choose 9. So 13, choose 9. And the answer is 715. 2 to the 4th is 16. And then you're going to have your x to the 4th. This is a negative to the 9th, so that's actually going to give me a negative. I'll just put it out there. That's 18. So there's what it wants. So it wants to know what the number in front would be. So let's multiply that now. 16. I would get negative 11,440 x to the 4th y to the 18th. There's no way anyone could argue and say that I'd like to say, oh, I like Pascal's triangle better. Well, you may. You'd be a half hour, 20 minutes probably figuring that out with Pascal's triangle versus less than 5 minutes doing it this way. Okay, let's look at, there's another one here. Combination, 13, choose. Let's figure out what we've got here. So 2x is the first term in our binomial. Negative y squared. I want to get y to be to the 12, so that means this has got to be a 6. So when you multiply those two together, you get your 12. Because this is a 13, if that's a 6, this has got to be a 7, which it'll work. Now I'm going to need a 6 here, and we will get combination. Let's actually do it out. So 13 choose 6. 13 choose 6 is 1716. 2 to the 7th power, so 2 to the power of 7 is 128. X will be to the 7th. Now this time it's a negative, but it's to the 6th power. So this is going to be actually stay positive, and you'll get your y to the 12. So it wants this now, 128 multiplied by 1716 equals, the coefficient would be 219,648, x to the 7th, y to the 12th. All right, I'm going to make up one more of those just to show you how it works. Let's take, okay, let's go, I don't want these to get too big. Let's go x to the 7th minus 2y cubed, and let's suppose it's to the 15th power. And I'm going to ask you, if you were to expand this all out, what would be the number in front of the term having x, y? Now I got to figure out what my exponents are going to be here. So let's suppose this is 27 and 42. Now you may have noticed I paused here for a second. You can't just randomly pick any numbers. If you're sitting there and you were able to, when I put a 27 here, knew this had to be 42, that's a good sign. You know what's going on. Now I'll explain how I did this. In my head, I was thinking negative 2y cubed. I knew my exponent was 15. So I said, I'm going to raise this one to the 9th. 9 times 3, so that would give me a y to the 27th. As soon as I put a 9 there, I knew that my other term, because it's a 15, remember the two together have to add up to 15, I knew this had to be a 6. 7 times 6. So that couldn't have been anything but x to the 42, or this would not work. So that's how I played around with my head to get these to work out. So for example, let's suppose I, in my head, said, I think I'll go with a 10 here. 10 times 3 would have been 30. I would have put a 30 there. If that's a 10, this would have to be a 5 now. And 5 times 7, this would have been a 35. Okay, so now let's set this up. So with a combination, it's 15 choose. We'll figure out what goes here in a second. Let's put our, I've already got it done up here basically, but in order for y cubed to become y to the 27, I need to put a 9 there. If I put a 9 there, I know I got to put a 6 there. This being a 9, this has to be a 9. So we are going to do 15 choose 9. 15 choose 9. And that gives me 5,005. Now I need the coefficient here, which is just a 1. So 1 to the 6th, that's just 1. And then I need negative 2 to the 9th power. So is a negative 512. My x will be to the 42, which is what I want. And my y will be to the 27, which is what I want. So then I just need to find the product of these. So 512 times 5005 will give me negative 2,562,560 x to the 42, y to the 27. There's my numerical coefficient. So I've now shown you a secondary way that you can expand a binomial in what's referred to as the binomial theorem, where you can use what we know as combinations. So you can see why I had to do a little bit of a sidetrack to at least show you what combinations were and kind of the a real crude evolution of these factorials and how it all kind of played in with combinations. And then once we had that formula and found that button on our calculator, it made us able to tie it in with the binomial theorem. All right, so that wraps up our unit on polynomials. So once you finish up this section and get your formative looked after on the binomial theorem, we will be ready for our first summative assessment on polynomials. After looking at your practice questions, as always, reach out if you have any questions or concerns, and best of luck with this material as we prepare for our first summative assessment. Thank you.